Right, our final topic in this module on momentum is actually angular momentum. And angular momentum occurs when we have an object moving in a circle. The linear momentum and angular momentum have definite correlations with one another, and so I put a chart up here on the board behind me to try and compare and contrast these two so that you can see how they're related to one another. So what we've been talking about so far has been linear motion. In this module I'm specifically referring to. In this module, we've been talking about linear motion where the objects are moving in a straight line. And so we've defined momentum as being the product of the mass and the velocity. And we know that if we exert a force over a period of time, we can cause a change in that momentum. We've also learned that if the sum of the forces acting on the system is zero, then momentum is going to be conserved. Okay, so all of this is for objects that are in linear motion. Now I'm going to move to rotational motion. So again, if you've got an object tied to a string and you're swinging it around your head, if you have a planet that's orbiting around the sun because of the pull of gravity, that's all rotational motion. And we've discussed some rotational motion already. Okay, so linear motion, now we're talking about rotational motion. So in place of momentum, I now have angular momentum. And he does go through a description in your book of why it's called angular momentum. I'm not going to go through that right now, but it's basically just a difference in terminology because of the angle that is made as you're moving around that circle. Angular momentum is abbreviated with a capital L. I don't know why they chose that, they just did. And so it's the mass times the velocity times the radius. Now, why does the radius come in there? Well, if we continue our comparison, we know that a force, it can affect the momentum, and we have already learned that torque affects rotational motion. And we learned that the equation for torque was the perpendicular force times the radius. So you should remember that from a module or two ago. And so what you'll see is that torque has this radius component in it, and so the momentum also has the radius component in it as well. So therefore, just like linear momentum can be conserved if the sum of the forces is zero, angular momentum will be conserved if the sum of the torques acting on the system is zero. So you can see that there's definitely similarities and correlations between the two types of momenta. Working the problems is very, very similar. We will look at example 9.6. We've got a child's toy made by tying a ball to a string and passing the string through a hollow tube, and the tube is then twirled to get the ball moving in a circle. Once the ball's moving, it says that they're going to hold the tube still, they're going to pull the string down through the tube, and the radius of the circle is then going to decrease. So then they give us initial radii, initial speeds, and they ask us what the new speed of the ball is going to be. Well, in this whole problem, what we have to look at is the fact that the momentum, the angular momentum before, is going to have to be conserved, and so it's going to be equal to the angular momentum afterwards. And we know that the momentum is the mass times the velocity times the radius in both cases. Okay, so do I know the mass? Well, I don't. They didn't give me the mass of the object that he was twirling, so I don't know m. I do know the velocity initially was 3.2 meters per second, so I can put that in here. And they told me that the radius was 34 centimeters, but so that my units match, I'm going to have to change that to meters. I'm going to assume you know how to do that. So that's going to be 0.34 meters. After he pulls the string down and changes the radius, the mass of the object that's twirling stays the same, we're being asked what the new speed is, but we do know that the new radius is 12 centimeters, which is 0.12 meters. Well, what have I got here now? Well, if you notice, I have mass on both sides, and so it will cancel out. So it doesn't really matter what the mass of the object is that's being twirled. It could be real heavy, it could be real light, it wouldn't make any difference because it cancels out. So now I have one equation, one unknown, so this problem is easy to solve. You're going to multiply 3.2 times 0.34 divided by 0.12 meters, and you're going to end up with a velocity of 9.1 meters per second. So again, that should make logical sense because since the mass is not changing on either side, if the radius is going to go down, the velocity is going to have to go up. That's just logical, okay? All right, so you'll get some practice with that, and we are at the end of Module 9.